Okay, so here we are at part 3. So hopefully you've just finished part 2 and where we learned about what standard error was. In this part, we're going to use standard error to build a confidence interval. First, like big surprise, we're going to have a question. So have a read through this, pause the video, work out which one you think is false. When you come back, we'll go through the answers together. Okay, so hopefully you've watched the standard error video already because this is going to require you to know what happened in that video. So standard error will be larger for smaller samples. So true. The smaller our sample, the more uncertainty, the more sampling error. And standard error is an estimate for sampling error. So it's going to be larger when we have less data. Standard error will be smaller for samples where the data is more varied. So the more variability, the more different stuff that's going on, the more unsure we are what the real picture is. Remember I used an example in one of the previous recordings where if I want to know what the favourite flavour ice cream is, and I ask someone and they say chocolate, and someone else and they say chocolate, everyone says chocolate, all the data is really consistent, I don't have much uncertainty. I know what's going on. I know the favourite flavour is chocolate. Whereas if there's lots of variability in people's responses, someone says chocolate, someone says vanilla, someone says hokey pokey, lots of variability, I've now got lots of uncertainty. So more uncertainty, more standard error, the more variability there is. So this one is the wrong way around. This is our false statement. C, a sampling distribution is a plot of many different sample estimates. So this is true. So far we've only looked at sampling distributions of sample means, but you can also build them up of sample proportions or sample standard deviations or medians or whatever you want. D, standard error is an estimate of how spread out the sampling distribution would be. And remember specifically, it's an estimate of the standard deviation of the sampling distribution. And E, our last one, we can estimate what the sampling distribution looks like using sample size and sample standard deviation. So the standard error for a sample mean is calculated by using those two things, the sample standard deviation divided by the square root of the sample size. And the reason those two things are really important is sample size and variability are the two things that affect how much sampling error we have. And what the sampling distribution looks like depends on how much sampling error we have. So if we can estimate how much sampling error there is, we can get an estimate for what the sampling distribution looks like as well. So we're going to introduce to you today this idea of a t distribution and a t multiplier. It gets quite theoretical. I'm going to try and highlight for you as we go through what things are really key to understand and what things are sort of a bit more complex and based on a lot of statistical theory. And so long as you kind of know that they exist, that's sufficient, but you don't have to understand them. So kind of just bear with me today. Don't panic. Don't freak out. Hopefully when we get through to doing examples in the next couple of recordings, it'll feel a bit more comfortable. So it's a lot of theory in this recording. So here's where we were at the end of the last recording. We'd discovered this magical thing called standard error. It's an estimate for how much sampling error there is. We're like, yes, because we've got lots of sampling error, we want a wide confidence interval, hardly any sampling error, we want a narrow confidence interval. So it's going to help us to figure out what to add on or subtract off to our estimate to build this interval, but we still don't know how much. Well, it turns out most sample means are no further than 2 standard errors away from the true unknown value of the parameter mu, or the population mean. And this is similar to the idea that we used back in chapter 1 to estimate our standard deviation. We know that most data are no further than 2 standard deviations from the mean of that distribution. Well, this is the same thing. Each of these dots, remember, is a sample mean, and the true mean is the mean of that distribution. So from our mean, this is a sampling distribution you're looking at there, sampling distribution when the sample size was 40. From that sampling distribution, if we take the mean of that, which is the parameter, and we go 1 standard error out either side and then 2 standard errors out either side, most of our sample means, most of those orange dots should fall in that range. So there's one, that's a sample mean, and look, it's less than 2 standard errors from the true mean. It falls sort of in this range. This one here, same thing. Oh my gosh, it's a sample mean, it's less than 2 standard errors from the true mean. What about this one? Okay, so it's more than 2 standard errors away, and that's a bit of a bummer, but it's in the tail of the distribution, so it's unusual that we would get a sample mean that small that it would be more than 2 standard errors away. So it's most sample means no further than 2 standard errors from the true mean. Let's think about this in reverse. So usually we don't have the whole sampling distribution, we don't have the population parameter, we just have one sample mean. One of those orange dots is all that we have. So if we flip this around the other way, we know that from a sample mean, the true value of the parameter is usually no further than 2 standard errors away. So here's a sample mean. If we go 2 standard errors up, 2 standard errors down, we capture the true value of the parameter in that interval. What about this one? Right, same thing. We captured the parameter in that interval. This one that was like really low, we didn't quite capture the parameter. See, there's like a bit of a gap. We don't quite make it. But again, it's quite unusual to get a sample mean that small, so we'd just be a bit unlucky. So 2 standard errors either side of a sample mean should be a pretty good confidence interval because it's probably going to capture the parameter. So that's what we do. We add 2 standard errors, we subtract 2 standard errors, and we get a confidence interval. So that's our formula at the moment for what we call a 2 standard error confidence interval. So here's a bit of a summary. So on the left side, what is sampling error and how is standard error an estimate for this? And then on the right, how we're going to use this thing, standard error, to build our confidence interval. And we're going to do an example now as well, so you can see how it works. So in this particular example, mu is a mean weight of a population of 521 males. Our estimate, x bar, our sample mean, is there. To build this confidence interval, we need the standard error. You will always be provided with this, but you can see over the side there how it would have been calculated. So to get our 2 standard error confidence interval, we take our estimate, we're going to add and subtract, that's what that plus minus symbol means, we're going to add and subtract, that's how we get the 2 ends of our interval, 2 times the standard error. So it's this bit here, the 2 times the standard error that we do first. So that becomes 3.026. 69.61 plus 3.026 gives us our upper limit. 69.61 minus 3.026 is going to give us our lower limit. So there's our confidence interval there. So we can do it. We can build this confidence interval. And remember, this is based on theory. So all this stuff back here is theory, right? The stuff it turns out, that's theory. So it seems to work pretty well according to our theory, but how well does it actually work? So we're going to have a look at this method and see how well it works when we build these intervals. So we're going to look at how well it works for different sample sizes. So we're going to start off with samples of size 36. Here, remember this is stats god mode. We now have access to the whole population, which normally would not happen, but for teaching purposes, to investigate this method. we're going to have the population. We're going to take samples of 36 and build these 2 standard error confidence intervals. And if we do that over and over and over again, we get these confidence intervals. All the green ones have captured the population parameter, which is usually unknown, but in this case we have the population, we know it. And the red ones are those times when we get unusually small sample means and our interval isn't quite wide enough to get the parameter, or we might have unusually large sample means, in which case our interval again isn't quite wide enough to reach the population parameter. So 95.3% of the time. Okay, so that's for samples of size 36, which is what we had in the example. What if we have a look at doing the same thing, but for samples now of only size 20? Now we know when you have a smaller sample, you have more sampling error, so the standard error is going to get bigger. So our intervals this time are going to be wider. Let's have a look. Okay, so you can already see those green lines building up down the bottom. They look a bit wider than they did last time, so that's what we expected. We're still getting a few red ones, but it's not looking too bad, I guess. But there's definitely a few more red ones than last time. And if we look at our coverage rate, 93.2%. So it's gone down. Let's go even further. Let's see what happens when we have a really small sample, like only 10. So again, our intervals got even wider because that standard error, our sampling error, is even bigger. So our interval's really, really wide. But on top of that, even though the intervals are really wide, sometimes they're still not making it to the population parameter. They're either too big, like this one over here, too high, or they're too low, and they're not quite making it. This time, only 89.2%. So in terms of our success rate, yes, as our sample size got smaller, we made the interval wider and wider because that standard error got bigger and bigger and bigger. So our interval being wider should have still been able to capture that population parameter, but it didn't. And actually these success rates, they're not good enough. And more importantly, they're not consistent enough. So a success rate of 95.3%, that's about what we had for our bootstrap confidence interval, and that's pretty good. We're actually totally fine with that. But as we go down for small samples, it's really dropping too low. And a sample size of 10, that's really not good enough. You're wrong, 10% of the time, or you haven't caught the population parameter 10% of the time. So what are we going to do? What do we do? Well, here's our formula as it stands right now. We can't change either of those two things. They come from the sample data, right? The sample mean or the standard error, which is based on the sample size and the sample standard deviation. So we can't change either of those things, but we can change this to. What do we change it to? Well, we don't want to just change it to like a bigger number, like 2.5, because then, sure, that'll be great for our samples of 10, where we need a really, really wide interval because our success rate wasn't very good. But for our samples of size 36, what will happen is we'll get these really wide intervals. Our success rate will be even better, but it was already fine. And then you've got this really wide interval that's kind of a bit useless. It's a bit Garfield, right? It's like somewhere between 0 and a billion. Like, it's not as useful. It's this balance that we have between precision, or how narrow our interval is, how useful it's going to be for us, and also our success rate, which comes down to how confident we can be that the interval has captured the parameter. So we want our success rates, we want these to all be pretty consistent. Around about 95% is pretty good. So we need to change this to a number, not that just that's a bit bigger, but a number that's flexible. So sometimes it gets quite a lot bigger, like when we have really small samples, or only gets like a tiny bit bigger or stays about the same as 2 when we have larger samples. This is where our t-distribution comes in. So the t-distribution is a familiar looking shape, and that green distribution there, that is actually the normal distribution. Beautiful bell shape, normal distribution. But the t-distribution isn't just one thing, it's actually a whole family of distributions. So you can see in the closet there's a bunch of different ones. And depending what situation you're in, you'll use a slightly different one. And the different sort of differences between all the different distributions comes down to this thing called degrees of freedom. So the normal distribution has degrees of freedom infinity. Degrees of freedom changes with regard to sample size. So degrees of freedom 5, that would be if you had a sample of size 6, right? You can see it's squished down a bit and it's fatter in the tails. Degrees of freedom 2, more smushed down, more fat in the tails. So all these t-distributions, and there's, infinity many of them, with all these different degrees of freedom, they're all slightly different shapes. So how can we use that to help us? Previously, when we had the bootstrap distribution as our estimate for the sampling distribution, where the width of it is telling us about how much sampling error there is, a t-distribution is basically that same shape, right? So instead of taking the middle 95% of a bootstrap distribution, we're going to take the middle 95% of the t-distribution. And when we drop down to the axis this time, it's going to give us these numbers, t, which are our t multipliers. So we're going to change that 2 to a t. Now what does this mean? How is this useful for us? So that middle 95%, if we have a distribution, I'm going to super exaggerate this, if we have a distribution instead that's got a smaller degrees of freedom, so this one here is degrees of freedom infinity. If I draw degrees of freedom 2, and I'm going to super exaggerate this so that we can see it, it's going to be squished down. Same kind of shape, it's going to have these fatter tails. And I know that my drawing isn't beautiful, but please bear with. It's not even close to symmetrical. But anyway, to get the middle 95% of that shape, because you've sort of lost this bit, it's going to end up over here and over here because the tails are fatter. So the middle 95% of that new one is probably going to come all the way out to here. So the t multiplier number is now going to be all the way out there at the new 95%. So the t multiplier for degrees of freedom 2 is bigger. And remember, degrees of freedom comes from our sample size. So we needed an interval that got wider when we had smaller sample sizes, which it did because standard error got bigger, but we actually needed it wider than that because we wanted to keep the success rate up. So that's what is happening here. The degrees of freedom means we get the curve that's correct for the sample size that we have, that gives us a t multiplier that's going to be the right size that will give us an interval, the perfect width, that it's going to have a success rate of 95% all the time. So here's how it changes. So this is changed to a t instead of a 2. And I'll show you how you get the t multiplier in a moment, but that goes in there. And you can see it's like a tiny bit bigger than 2. But that tiny bit makes a real difference. So that multiplication is going to change a little bit. So this bit changes a little bit. And our interval, if we compare it to the last one, it's just slightly wider, right? A little bit lower at the low end and a little bit higher at the high end. So where can we get this t multiplier from? We can get it from the t procedures tool. So the t procedures tool is going to be linked on Canvas, and it looks something like this. We're looking at a single mean, so you pick that one to start. you just need to put in your sample mean and your sample standard deviation, which in our case was 9.08, and your sample size. And it gives you your standard error, so I told you never have to calculate it, there it is, and your t multiplier. Okay, standard error, t multiplier. So let's see how well this works, because if we went through all that work and it didn't actually help, that's not going to be of much benefit to us. So we're going to switch now from a 2 standard error interval to a t standard error interval. We'll go back to samples of 36. So 36 worked pretty well anyway. The t multiplier now has changed from 2 to 2.03. It's got like a tiny bit bigger. So all of these intervals down here are like a tiny bit wider than they were before. You're not even going to be able to see the difference. How's our coverage? What's our success rate? It's looking pretty good again. Not looking too different from before, but our intervals haven't got much wider than before. So it's not really rocket science here. Wait for it to stop. There we go. 95% bang on. How's that? Okay, let's see what happens now if we go to samples of size 20. So this is where the issues started. Our intervals got wider, yes, but they didn't get wider enough. So we need an interval that is wide enough that it's going to capture that parameter. So here's our coverage again. It's running really slow. Here we go, 93.6%. Let's try samples of size 10. So samples of size 10, previously when we did our 2 standard error interval, they got really, really wide, but it still wasn't wide enough. And our success rate, or our coverage, was less than 90%. So really not good enough. We can already see that it's looking a lot better than that. Okay, 94.6%. Okay, so this is a simulation that we've just viewed, taking samples over and over again and getting new sample means and building these t standard error confidence intervals. So if we ran it again, these success rates would change slightly. But what we're seeing is that all of these numbers are pretty darn close to 95%. So by changing the multiplier from 2 to t, we've managed to make our interval width flexible depending on the sample size. So now what we have is a formula for a confidence interval that if we use it, it builds a confidence interval that we can be pretty sure it's got the population parameter in it about 95% sure. So here we go. So we've changed our formula now to include this t, the description of what that t multiplier it is, and what the whole benefit of it is. So using a t multiplier, our confidence interval will always be as successful as the specified level of confidence. So we've tried to get all of our intervals to be 95% confident that it will hit it. I just want to show you one more thing. Oh, I closed it. Let's go back to the T procedures tool. So we had a single mean of 69.61 and a standard deviation of 9.08, a sample size of 36. So the t multiplier was just a little bit above 2. If we drop this down to like a sample of size 10, look at how much that t multiplier jumps up. So that number's jumped up, which means this bit here is jumped up, so that whole bit there that you're going to add on or subtract off, right? This is all going to be bigger. It's going to make your interval much, much wider. So the T procedures tool is where you're going to go to calculate that T multiplier for your confidence interval. Okay, so what is the T distribution? It's a shape, it's a distribution, it's a theoretical distribution, and it's what we're going to be using to estimate the sampling distribution. Why do we need a T multiplier? Because just using 2 wasn't that great when the samples got quite small. We wanted something with flexibility in it. How do you calculate a T standard error confidence interval? Using that formula, and there are more examples in the coming recordings, so you can wait for that to see how we do it. And how successful is a T standard error confidence interval? In the case that we were looking at, it was almost always 95% successful. So it's a pretty consistent success rate. Okay, that takes us to the end of part 3. So part 4, we're going to see some examples.